How about stronger materials? You know, we see ads like this all the time from Glidewell. And I have to ask you, what are we really interested in? Are we interested in impact load or static load in terms of what drives failures? And the truth of the matter is that we're really interested in static load, just constantly loading our restorative materials. Remember, materials resist compression and way stronger under compression than tension. And this is how they determine the strength of zirconia. Right? They use a 3-point test. They take a sample of a known length and a known thickness, support it on both ends, and press in the center until it breaks. Well, it doesn't break on the top because the material is very strong in compression. It cracks on the bottom because that's where it's under tension. Now, there aren't a lot of systematic reviews of zirconia FPDs. They just really haven't been out there that long. But I found one by Mazza. And 4 studies met inclusion. What's interesting is the one by Garling, and I want you to look at the mean follow-up, 167 months. Most studies don't look at things this long. But this is kind of critical when it comes to long-term determination of what works. So here's the forest plot, which is just comparing all 4 of the included studies. And if you look at Garling, high failure events. Okay, 12 failed out of 36. That's pretty significant. And what you need to understand is that fatigue and crack propagation in zirconia, right, in clinical aging takes time. And this is what we don't have sometimes. It can be a big problem. But let's try to understand, again, the concept of law of beams. This is from Glidewell's lab page. And what they're talking about is whether you can make a zirconium FPD. And what they said is when considering the cross-section of the connectors, the load-carrying capacity of a bridge is proportional to the height of the connector multiplied by the width. Okay, and so this number should be greater than 27 millimeters, so the height squared by the width. In other words, this is a practical example of the law of beams. If you double the horizontal component, you get double the strength. But if you double the vertical component, you get 8 times the strength. Now understand, zirconia can and will break. And I want to share with you a couple of my cases. And this is one of my cases. And I want you to take a look at the size of the zirconia, just outlined in red. I mean, this is more than 27 millimeters squared, but yet it fractured. And why did it fracture? It fractured because of manufacturing. And Quinn, in his study of analysis of broken ceramic dental restorations, gave me the answer. This is a thermal fracture. Okay? And the interesting thing is, when a fracture starts in zirconia, it does not have to be catastrophic. In fact, the problem is that the fracture will start and then it radiates in steps. So it takes a while for complete failure, catastrophic failure to occur. Let me share with you another case of mine that broke. And this broke after a year in service. Again, pretty beefy zirconia connector, okay, overlaying ceramic. But let's take a look at my design. Take a look at the red arrow point. And Quinn also looked at something like this. And the problem is that too much stress was created at this sharp point. And if you look at the way it failed, the cracks grew in stages. You can see there were 3 stages of fracture before it catastrophically broke. So these are the difficult things we talk about, the interactions of our materials. So just because they tell us it's strong doesn't mean it's strong. I finally want to share with you, when it comes to zirconia, a great study done by my dear friend Suleiman. And what he did is they created different specimens of different thicknesses of 3Y, 4Y, and 5Y zirconia. And they loaded them with biaxial testing and repeated 1.2 million cycles. And that's the equivalent of 5 years of wear. And then they tested them. And so they looked at 3Y, 4Y, and 5Y. And different preparation thicknesses, 0.7 millimeters and 1.2. And they measured the baseline strength and the strength after fatiguing it. But what's important to understand is that a number of specimens fractured before completion of their simulation. Take a look at those numbers. 50% of 4Y at 0.7 millimeters failed before the study was completed. 85% of 5Y zirconia, 0.7 millimeters thick, failed at 85% before completion of the study. And even the 1.2 millimeter thickness 5Y, 36% of the samples failed before completion of 5 years of wear. So the